Hello, everyone. Today I'm going to start talking through chapter 6. These slides, this next series of unit of about 11 or 12 videos, I think by the time we're done, are going to go from chapter 6 all the way through into parts of chapter 11. I find that material likes to build off of itself. And I know this is a different style and approach than what is being used in lecture. But I hope that in combining these that you can go back and use these videos for chapter 11 whenever you get there in lecture. So let's get going. In this first video, we are going to really just talk through some conventions and some definitions when it comes to playing with calorimetry and energy flow. So to start off with, definitions. In this unit, in this chapter block of stuff, we are going to talk about energy, work, and heat. And heat. Energy is defined as the capacity to do work. So work is the result of a force acting through a distance. And so that's something moving. Heat is the flow of energy caused by a temperature difference. Okay, these are very esoteric sort of physics style definitions. As we get going through, we are going to begin to understand what these definitions are for chemical systems and what does work look like in chemistry whenever we aren't talking about, I don't know, someone's CrossFit where they're dragging a tire. That's not how chemical work happens. That's more of a physical work. And so we're going to try to define the stuff more in terms of chemistry. So when we think about energy, there are really several types of energy. There's kinetic energy, which is the energy of motion. So kinetic energy is dragging that tire across the room, moving something. Thermal energy is the energy of temperature. Now, kinetic energy and thermal energy are very, very similar because temperature is really just a measure of the average kinetic energy. So temperature really is motion, but this is motion at the molecular level. And so in a solution, our molecules in a solution that is at higher temperature, our molecules are moving faster. They have more kinetic energy than, say, ice water. Okay? Potential energy is the energy associated with a position or composition. And so in chemistry terms, if we think about our energy level diagrams from when we talked about atoms, that we had electrons in an orbital. That orbital those electrons have energy, and that is the potential energy. The other way that this is described is if we have a cliff and we have a ball or an object on the top of the cliff, that it has the potential to fall down. And so that object has potential energy. Chemical energy is a type of potential energy. It is this energy that I was describing here. It's the energy associated with the relative position of the electrons and nuclei in atoms and molecules. And so that's where our electron configuration and our MO diagrams and our atomic energy level diagrams come into play. Okay, in this section, we are really deep down, everything that we do is going to be looking at the first law of thermodynamics. The first law of thermodynamics states that energy cannot be created nor destroyed, only transferred. So the energy that is contained within a system is going to stay that amount of energy no matter what you do to it. That energy can change forms, but it's not going to multiply or diminish, disappear. So, some other terms. When we talk about the first law of thermodynamics, we define things as the system, the surroundings, and the universe. So the system is the thing that we are looking at. Oftentimes this is what is inside of the beaker, but it's our perspective. It's what we are asking, what happens to this thing. The surroundings is the area outside of our system. And so it's what our system is in direct contact with. The universe is everything. It's the system, it's the surroundings, it's even this area outside of the system. It's absolutely everything. And so when we think about energies, the energy of the system plus the energy of the surroundings is going to equal the energy of the universe, because we can't create or destroy energy. So in chemistry, we really like to use the term internal energy. We tend not to separate the kinetic energy and the potential energy because oftentimes in chemical systems, we really only can get a measure of the total energy. And so the total energy, also known as the internal energy, is the sum of the kinetic and the potential energies. So our total energy or our internal energy is equal to our kinetic energy plus our potential energy. And this is true in physics as well. In physics problems, you divide up and you solve the kinetic energy portion and you solve the potential energy portion completely separately. We do this as well in chemistry, but oftentimes in chemistry, what we really are looking at is this total energy value. So another thing that we are going to be dealing with in this chapter are what are called state functions. State functions are any function where the value of that answer, that thing that we calculated, is the difference between the final condition and the initial condition. And so we can say something like delta E, which is a state function, is going to be E final minus E initial. And so we can think of that as the difference in energy of the car at the bottom versus the car at the top. That difference in energy is the same whether or not this person pushed the car up the ramp all the way to the end, or if they took the elevator and went to the end. That the state function, the difference in energy, is the same because the final spot and the initial spot are the same. And so state functions do not take into consideration the pathway in which the process happened, just the final state and the initial state. So there are lots and lots of ways to be able to represent energy flow. Myself, I like using energy level diagrams, which are these here, where I have a certain energy state. This would be a total energy state for my reactants, an energy state for my products, and I have a transition that occurs to go from reactants to products, and that transition has some amount of change of energy, or delta E. Other people like to look at more of these energy flow diagrams, that energy is moving from the surroundings to the system in this example. Either way of representing is fine. So in this example, we have an endothermic reaction, which is defined as energy is added to the system. Endo goes into the system from the surroundings, or that the products have more energy than the reactants. It's opposite for endothermic. Endothermic, the delta E of the system is greater than 0, positive. The opposite is what is known as an exothermic reaction, and that's where the energy flows from the system to the surroundings, or that the products have more energy than the reactants. So in exothermic systems, the delta E of the system is less than 0, so it's negative. Okay. So in energy conservation, first law of thermodynamics tells us that the change of the energy of the system has to be opposite of the change of energy of the surroundings. So if we thought about our energy flow diagrams, that we would have system giving energy to the surroundings, or vice versa. And if the system is giving energy to the surroundings, that means that it is exothermic. But that also means that the surroundings is taking energy from the system, which is the opposite, which is endothermic from the perspective of the surroundings. And so with this, our system and our surroundings are always going to be opposite of each other. Something is going to have to give energy, and something is going to have to receive energy, because energy is conserved. But to keep things simple, we will always discuss from the perspective of the system. And so we will always, when we are looking for delta E or other values that we're going to learn about in this chapter, it is always going to be from the perspective of the system. Okay, hopefully this gave you some of the language and the definitions that we are going to be using throughout this chapter. In the next series of videos, we're going to learn more about how to measure these values and how to do calculations with how these numbers and calculations help us to make conclusions on systems. Okay, I hope to see you back for the next installment.